Thank you, and thank you so much, everyone, to join. I'm on leave now, I should say, from the university to build this company, zkConduit, to build this product, Ezekiel, which, as you see from the initial slide here, is something you can install in Python. And our goal with this is to make zero-knowledge machine learning and zero-knowledge in general more practical. So I'm going to do some slides and hopefully keep your attention, and I'm going to pass it on to Jason for the demo since he's there in person. I think those things go better that way. So let's get started. So, okay. One of the kind of central issue that we're dealing with is kind of the promise of blockchain, right? All of the things that we imagine we could do are not, we haven't been able to quite deliver them. And part of that is just normal scalability problems that we're addressing with L2s and everything else. But part of it, I think, is deeper, and it has to do with compromises that we've made in order to achieve consensus. It even has to do with the speed of light. And those things are things that can be addressed by adding in another ingredient, which is these zero-knowledge proofs. They offer a kind of composability without consensus. So without this, we in an expensive consensus environment, we're really limited to kind of simple math, right? Elementary school math, we can fit into a smart contract that doesn't explode the size of the contract or the amount of gas. And it means that we really have a lot of restrictions from the EVM. We come up with some kind of great algorithm we want to run, and then we find, oh, the contract size is too big, or we run out of gas, stack is too deep, maybe we put it to L2, or maybe we settle for kind of decentralized and name only, and we actually run everything in a Postgres database, and we keep the state somewhere else. And the exciting thing about ZK is it's a way to scale what the EVM can do, but it's also really kind of opens up a bigger solution. Because I think I'm echoing. Everyone could just mute for the moment. Glacier, I think, perhaps. Okay, so ZK, together with smart contracts, expands the space of what's possible, both in terms of just simple scalability. We could do something like a roll-up, but also in this sort of deeper sense, and I'll talk about it more later, where we really have kind of both qualitatively and quantitatively different capabilities, and that the two things combined, their knowledge proofs and consensus, can create a lot of really interesting constructions that solve a lot of problems and kind of just help us deliver on the promise of blockchain. Of course, the catch is that working with ZK is very difficult. So, right, I'm a math professor, lots of PhDs floating around, and it's hard for us and it's hard for everyone to deal with these circuits. And so what we're seeing now is this emergence of a bunch of projects, of which Ezekiel is one, where we try to take this part of the problem away for you and solve it for you, so that you work in a simpler language, or not a simpler language, but work in a language that's more familiar and make use of programs that you've already written. And one way to think about that insight is, what is the most, so circuits are an awkward programming paradigm, but there's something very similar that we've seen get really wide deployment, especially with this recent growth in AI, incredibly wide deployment, which is neural networks. So a neural network is a computational graph. We take a bunch of nodes, inputs, parameters, we apply a bunch of operations to them, and we get a result. And we do it in a way that's differential, and that lets us learn, right? That lets us fit the parameters. But that means that there's a vast installed infrastructure of human knowledge and computer programs that work with circuits. So we decided to go after these things as the right primitive to start thinking about ZK, right? So Ezekiel is first and foremost a program that transforms a computational graph like a neural network library baked into an Onyx into a circuit, a Halo 2 circuit, and then that lets you create proofs and verify proofs against it. But instead of writing those circuits, now you can just write Python, or you can, if you don't even want to write Python, you can throw together a bunch of matrix multiplications and rulers and train a model to do the task for you, or that's increasingly the way we are solving problems with general purpose AI models, and this lets us sort of port that into the UVM world. And our goal, of course, is to make this combination of zero knowledge proofs and smart contracts into something that's easy to work with. Let me stop for a second and talk about some of the cool things you can build. We've seen a lot of uptake with hackathons and hacker groups like this one. So for example, DeFi Vaults, there's a picture here of the folks from Noya that are using Ezekiel and won the ZK Day competition in Paris. People are building on-chain credit scoring, people are working with generative NFTs, a lot of really interesting things with games and autonomous worlds that we're doing in partnership with Lattice and Xerox Park. Sort of fun on-chain games like a demo application that Jason will talk about a bit more, which is called cryptoidle.tech. That's just a little application that we built to demo some of the technology. And I think long-term, of course, identity and account abstraction are some of the most important themes. Well, I like to say that with Ezekiel, you can kind of build your own world coin. If you don't like the way that that's worked out, or that cryptoeconomics, or you find that we're creepy or whatever, this is a tooling that makes it easy to not just decentralize identity, but decentralize kind of control of identity. And there's a lot of use cases around oracles and apps in general that can use off-chain data. So I like to say the zkML technology that gives blockchain eyes, right? Lets it see and perceive the physical world. So this is cryptoidle.tech if you want to check it out in another window, or if you want to check it out afterwards. And once you run these proofs, the cryptoidle proof, the cryptoidle game, you sing to it, it rates you and performs a proof of that rating. So you get entered into a leaderboard, and the zkML proof takes about 2 seconds to make a judgment. And then to verify that judgment on Polygon only costs about 4 cents. So costs are actually quite reasonable, at least if you use L2. They're getting better on mainnet sort of slowly. So let's talk a little bit about some of the drill down a little bit more into the concepts that are behind Ezekiel. And then at the end, I'll sort of slice through again and talk about kind of how do you practically use it. So you can think about, I like to start with digital signatures. So most people in blockchain, of course, are familiar with digital signatures outside blockchain, but the very idea of asymmetric cryptography is kind of difficult. But we all know what an ECDSA signature is. And programmers, both inside and outside blockchain, have been able to produce amazing construction using just digital signatures. Authorization and revocation, certificate authorities, a bunch of pieces of foundation of the modern internet. But I'd say the problem is that what we do now is we program kind of with digital signature. The digital signature is a primitive. We write a whole bunch of code on top of that, and we think through the system on top of that. And that leads to quite complex constructions. It leads to chatty protocols like consensus algorithms. And the problem with chatty protocols is that, even if you use something like MPC, whenever you have to communicate around the world, I have to talk to you in Singapore. For humans, it's not that bad of a delay. 150 milliseconds is nothing. But for a computer, 150 milliseconds is an eternity, right? And being required to use these kind of chatty protocols means that there's sort of a fundamental limit on how fast we can go. And using ZK, we can kind of remove that limit. And they also have kind of limited security models and privacy options. So we're stuck with someone has to hold the key. Someone has to be the root. Someone has to hold the private key. You have to keep track of it on a ledger, or trust someone else to hold it for you. And ZK technology kind of helps us open up the space of other things we could possibly do, other ways we can model authorization and identity. And the way I like to think about this is it lets you program instead of with digital signatures as a tool or primitive. It lets you write a program inside of a digital signature and retain the cryptographic properties. So a typical signature algorithm, so you can think about ZK proof as a programmable signature. And a typical signature algorithm, you have a secret key, you have a public message, and you hash the message, and you sign it with your key according to a signature algorithm. That signature algorithm is something that everybody knows and is fixed in advance, and you get out a signature and a public message, and then you pass that on to verify for verification to the chain or to a counterparty, right? Then with zero knowledge proof, what you do is you get to replace kind of the secret key with arbitrary private inputs. You get to replace the public message with arbitrary public inputs. You get to replace the signature algorithm with any program you like, any program at all, and you get out a proof instead of a signature, and you get out the public parts, and then you pass it on for verification. And it has similar security and privacy, right? So zero knowledge proofs were initially described as kind of probabilistically checkable proofs, right? Which doesn't sound very good until you realize that the chance that you're going to be able to create a fake proof is more like the chance that you'll be able to guess Satoshi's keys than the chance that you'll win a coin flip. And so I think it's something that we can all be comfortable with, or eventually get comfortable with. Yeah, and then narrowing down to zkML, that just says the program that we're going to put in this any program box that lets us do anything we like is specifically inference or forward passes or training passes in an AI or machine learning model. And that's the focus of what we've shipped so far with Ezekiel. So the other kind of big picture thing I want to throw at you is when you're doing whether it's a hackathon project or a startup, right, it's important to time things right. Being too early is as bad as being too late. And why is it that ZKPs and zkML are getting a lot of attention now? Why is it a good program time right now? And it's kind of because they've been steadily getting faster and more practical for at least 8 years or something, depending on where you count the starting point, maybe even longer. And they're just now kind of hitting this inflection point where you can really do practical things. There's ways, languages that let you work with them in a simple way and program comfortably, like Ezekiel compiling to Python and other special purpose languages. And they're just kind of getting faster and faster in a very rapid way. So concretely in Ezekiel, we've gone from, we like to think about how many floating point operations can we fit in one proof, right? Rather than floating point operations per second, it's per proof. And that has gone in the space of the past year from around 100 or 1,000 to on the order of 100 million. So representing a huge speed up in time and a huge reduction in memory usage. And that continues. So like just in the past week, the memory usage for some parts of the proof have actually gone down by 75%. Another way to think about it is, and this is a little bit more abstract, is kind of proofs per chain transaction, right? So if you think about, in a sense, what's happening in the rollup is, if you think of each transaction as being like a proof, of course it is, because a signature is an example of a zero knowledge proof. If you pack 1,000 signatures or 100 signatures in one transaction, then in some sense, you've got 100 proofs per one transaction. Another thing that you can think about as being in this category is something called ZooPass, which was built for Zuzulu by Xerox PARC. And that let you enter events and by producing a zero knowledge proof. So for that situation, you might have one blockchain transaction, buying a ticket or something, and then 100 or 1,000 times that you use that kind of identity, prove that you are a member of a group. So you have sort of on the order of 1,000 proofs per transaction. And the hypothesis is that over the next few years, with improvements in ZKP efficiency and dev tooling and kind of new application ideas, we're going to see that also scale kind of 100 million, billion proofs per blockchain transaction. And so in this upper right corner where we have, 1 billion flops per proof and 1 billion proofs per transaction, there's a lot of interesting things that could happen. And, we're sort of in the business of chewing the glass to make sure that this is possible, rather than thinking of, what cool things to build there. So I'm going to punt that to you. Think about what might make sense in that quadrant. Of course, we have ideas. They're probably wrong. The world just needs to search and iterate and find those applications. So one way to think about it is as a transition that's not so different from kind of the PC mainframe world the mainframe world to the PC world, right? So like early days of computing, there's a picture of IBM 360. Computers were mainly used for the same ZK is used today, which is for rollups, right, or for financial transactions, rollups, exchanges, privacy protocols, COBOL inside of a bank. And we're reaching the point where ZK is so practical that we're starting to get into kind of PC era or the internet era, where we can think of a lot of wacky stuff. We can mess around with games. We can put, 100 million parameter models or billion parameter models on chain. We can build personalities that have their own life. We can do on-chain physics simulations. We can do a lot of crazy stuff. And so it's a really interesting kind of moment. And a perfect moment, I think, to build with this stuff. Okay, so now we're going to get into the third section of my discussion, which is practically, if you buy what I'm selling or what I'm saying, and you think that is a good time to build, what steps do we actually do? What is it like to build on Ezekiel? And I'm going to lay it out a little bit, but after this, I'm going to pass it on to Jason, who will give you kind of the hands-on demo. And I know he's already helped some of you work with this. So you can think about Ezekiel as an engine that lets you run models or run computations. So you want to run some kind of statistics or an AI model or some other computational on-chain graph on-chain, but it's something that doesn't fit. Or you want to run this function and you want to keep some of the input secret, or you want to keep the function secret, the model itself. So let's say we have a Python function, result equals forward. I like the word forward because it's the one we use in an ML model, an AI model, forward of input. And so what Ezekiel does is it's a compiler. It takes forward this function that you've defined and turns it into two pieces, a prover that takes the input and gives you back the result. And then it gives you this kind of hex, meaningless, random looking string of hex digits that is the proof. Then we have a smart contract that's also produced by the program that lets you checks that hex, that seemingly random sequence of digits, and lets you determine if it is in fact true. If you can believe, if you can trust, if the chain can trust that the result is equal to the forward function applied to that input. And this lets you do arbitrary computation as if it was done on chain. So as the app developer, it's your job to define the forward function in Python. Of course, we can give you some hints. Here's an example of a small neural network, a couple of convolutional layers, a couple of linear layers alternated with a ReLU linearity that you can use to learn, MNIST or classify audio or do whatever you like. And then once that thing gets transformed into a proof by Ezekiel, you can kind of, I'm going to go over a couple of typical questions we get asked. So one is, how much gas does it take? Right now, it takes around 400,000 gas. And that varies a little bit depending on the size of the proof. How fast to create a proof? Well, this varies a lot. So something like crypto idle that's listening to some audio or an audio spectrogram and classifying it takes only a couple of seconds. Small machine learning models take seconds. Large machine learning models, transformers, stuff like that are going to take minutes. And even some things will take hours. So it depends on your application and how much data you'd like to prove against. If you wanted to prove, for example, I have a model and I'm going to run it on 10,000 data points or 10,000 data frames, examples, like 10,000 resumes to prove that my resume screening model is unbiased. That's going to take a long time in aggregate. Another question you might ask is, can parts of this thing be kept secret? So yes, the answer is that this hex, the proof, shows that the prover, the person who's constructed the proof on their local machine or remotely, knows the input and or the forward function such that the result equals the forward of the input. And this can happen without revealing the input or the forward to anyone. Now, there's some right now with Ezekiel, there's some boilerplate associated to exporting the model, because what we do is we use this common representation called Onyx, which is just a frozen abstract syntax tree of a forward model. In Torch, this is what it looks like to export it. It's more or less the same every time. In Keras, this is what it looks like to input output to export this Onyx. So it's a little different for each framework, but it's just a little bit of boilerplate. And other question you might ask about this thing is, okay, what if I want to sort of partly reveal the input or partly reveal the output or partly reveal the parameters? Like maybe I have a trading strategy that I want to put on chain. And what I'd like to do is commit to the strategy and then, but not reveal it, not give away my alpha, run that strategy for a few months and then say to people, oh, hey, look, this is how my strategy is done. You can employ that strategy as well, right? Without revealing what it was. So in that scenario, you would commit in some way to the strategy. So in this case, you would, for example, hash the weights of the parameters in the model, and then you prove that you know the input and the forward, such that result equals forward input. And any of these things can be replaced by hashes if you want kind of a commitment, or they could be signed if you want, for example, data that's been attested to by someone. Another question we get is, can we run the proof for you? Of course, yes, we can run the proof for you, and we have some infrastructure for doing that. That's in kind of a closed beta that I'm happy to talk to you about. Other questions, can an input to these models be uploaded by a user? Yes, that's what happens in a crypto idle. Can it be a query against the database? Yes, we have an example of a database query. So that's a really interesting direction for getting all kinds of off-chain data on-chain. Can it use current on-chain state? Yes, and we have some tooling for that. Can it use historical on-chain state? It doesn't come from a database, not quite yet, but soon we will have some tools for that as well. Okay, so suppose you defined a function, you know what you want to do, and you've thought about the crypto system, what needs to be hashed, what needs to be signed, what needs to be attested to. What you do next is to generate some artifacts that can be proved against. So these are kind of cryptographic objects that the prover will need, and you're going to create a solidity verifier that will be your sort of source of truth as to whether or not you've proved it or not, and probably you're going to want to deploy the verifier, although in some cases you don't even need to do that. And of course, you need to tell the prover where to find the ingredients they need to make a proof, and you need to tell anyone who cares to verify it where to find the verifier. And then usually you're going to be deploying this in the context of a larger smart contract network or a larger application. And so you just wire the smart contract, your verifier contract into the smart contract. Usually that means something like smart contract is executing. At some point it wants to change state using the result of the proof. The proof says, this thing is true, so change the state, send this money to this person, or update the state of the game, or do a tick of the Minecraft or whatever. So you check the proof is true, then you change the state on chain. And so usually the call to verifier contract is just a very simple require somewhere in your contract. So, okay, to do this stuff, what you're going to need to do is to generate some settings and calibrate them. And that's kind of tunes the quantization strategy that we're using for Ezekiel in order to transform floating points into fixed point arithmetic in a way that's stable. And then we're going to want to run a setup, which creates these prover and verifier cryptographic artifacts. And then generally you want to create a EVM verifier to act as your source of truth as to whether or not the proof has been computed. And that's the thing you're going to deploy and call from your contracts. We also have a JavaScript package called Ezekiel.js that's very beta, but I encourage you to check it out and give us feedback. We're quick to fix things if they're broken or they're not doing what you expect. And so with Ezekiel.js, you can quickly plug in all this infrastructure into your app. And if you want to use our proving server, you can plug that in as well. And then you can very easily build something to submit things on chain, like crypto idle. So for more examples, I invite you to check out examples on GitHub, especially the notebooks. There's a bunch of IPython notebooks that walk through flows. And Jason is going to walk you through one of those that he created just for you. If you have questions, we have a Discord and we have a Telegram. Please jump in and ask questions, or ask us directly. Okay, so that's it. The last thing is that we have this hub product that we're working on, collaborated with a few early users, and if you're interested in that, just let us know. That will help you kind of outsource proof generation if that's something that you don't want to have to deal with. But this is an open source product, so you're always free to create your own proofs. We're just trying to add a few services that will make life slightly easier, as is in our name. Okay. That's all I have. Maybe we can have a few questions before I pass it to Jason for the demos. Let's see the chat. On-chain performance is the proof effect.
Hi, Professor Morton.
Yeah.
Great presentation.
Okay.
It's kind of incredible that you've been able to scale the number of flops in the proof, right? Can you maybe comment on the optimization techniques that has maybe enabled this? Is there some specialized tuning being done in the underlying proof system?
Yeah, so there's a bunch of stuff that, so I often say that I really think that, so there's a lot of things that are happening in ZK right now. There's a lot of sources of advantage. And one of them is that there's a constant stream of great new research coming out. For example, lots of new lookup arguments that are slowly getting incorporated into the production systems. But there's a lot of even lower hanging fruit than that, in the sense that these systems were created for a particular purpose, right? So we use, there are two in the back end. It was created to run the orchard circuit for Zcash, and it does a beautiful job of that. However, when you change the type of circuits that you want to plug in, it's sometimes not optimized for that. So the components that make it faster are, one, kind of rethinking the type of argument that we make. For example, how do we represent matrix multiplication, or how do we represent a dot product? How to move things between different parts of the proof, like just the sort of small ball laying out. It's a bit like programming with very little RAM. It's like you want to go to the moon and you have 16 kilobytes. How do you fit everything efficiently as possible? So it's a lot of that kind of just golf and programming. And also there's been a fair amount of work that our team has done, particularly Dante, on improving some of the parts of Halo 2 that are blockers. So for example, if we start to find that witness generation is too slow, or something isn't as parallel as it should be, then we'll rewrite the parts of the code that need to be changed in order to improve parallelization or memory pipelining or whatever. So it's just a lot of, not silver bullets, but lead bullets, just doing the engineering work. And fortunately, there seems to be quite a lot of juice still left there.
Makes sense. Thank you. I actually had one more question. So does Ezekiel support creating these proofs for verifying the fairness of the model training as well, in addition to inference?
Yeah, so you can verify fairness in the sense of, so there's a couple of questions that I want to unpack there. One is that, do you really want to check the way that it was trained, or do you want to check the way that it behaves? So for example, if you're trying to prove that a model doesn't exhibit, doesn't discriminate, right, doesn't exhibit an unfair bias, then you're going to want to have a test set, a train that you want to show the model is within certain parameters on that test set, right? So that's fully supported right now. Training requires two things. One is being able to prove the backward pass, which we just haven't implemented, but it's kind of not that hard. We just haven't had that much demand for it. And then it requires a lot of patience, because it's, a typical model training has many, many runs. And so if you're applying a big overhead, then it's going to be quite a long time to get that done. But I think it's something that we will probably end up supporting sometime later this year, perhaps. Or when someone comes to us with a really compelling use case where they really believe that training is necessary, then we might do it faster. Maybe that's you.
Thank you.
Yeah, if you have any questions, feel free to drop in the chat box so that we can review the question one by one. And also for those of you who stay offline in the office, feel free to drop any questions.
Yeah, there's one question in the chat box from earlier. What on-chain performance does the proof affect? Maybe you could clarify, St. John, what I'm just not sure. What you're asking. I mean, one thing you might be asking is what happens when the proof is verified? So that's sort of up to you as the smart contract developer. All we sort of give you back is true or false. You know, did the proof verify or not? The other thing you might be asking is, what are the on-chain costs of a proof? How do they scale? And it's very lumpy. So of course, we mostly want things to fit inside of a smart contract byte size limit and inside a gas limit. There is, at some point, the model of proof can be too large and can start to squeeze outside of that. But there's a pretty large sort of fixed cost that, and you can fit most things inside of that fixed cost. Not quite as good as Gross 16, which is just like an absolute, you know, fixed cost. Oh, up to a certain limit, but it has a limit. Okay. Another question: are concepts like recursive proofs and folding schemes used? No, so we're not using either of those yet. Definitely looking at it. So new lookup arguments, recursive proofs, folding schemes. You know, excited to get those things plugged in as they come into kind of ready for production. Two things that are important to us are why we've been a little bit conservative about that is that, of course, we're focused on things that can verify on the EVM. So if there's no EVM verifier, it's not ready yet. And then the other thing is just, it takes a long time for a new proof system to get from idea stage to production stage where you feel comfortable. And one of the nice things about Halo 2 is that it's used by a number of groups and it's been in production for a while. So we're pretty comfortable with Halo 2 as the proof system. And we'll be, you know, incorporating some of the other stuff as it kind of comes down the pipe.
A short demo to show how to like run this whole like the whole framework and like how to given a certain input and how to generate a certain model and also give like upload this to the on-chain, something like that. Maybe just a very short demo.
Yep. And I was going to pass it to Jason for that since he's there in person. Is that right?
Yep.
Okay. I'm going to stop my sharing so that you can share. Thank you.
It might be echo. I'll put you guys on mute.
Oh, hi guys. Okay, there's a weird echo in the actual venue itself, but I'll be going through the demo for Ezekiel. Okay, let me share my screen. Okay.
If you turn off the speaker on that side,
I'll move to a different place. Okay. Hey guys, I'm in a different venue now. Okay, so this is the crypto idol demo that we were talking about just now. So it's kind of an example of how you can actually run zkML on chain right now to run inference of like the voice. So you don't exactly need to do like zkML for just DeFi applications. There are a bunch of things you can do. So one of the crazy ideas that we thought of was like, what if we did an on-chain voice rating application? So I can demonstrate it right now. So I can click record and sing, hello, hello, hello. Okay. So, okay, this is what I've sung. And if you click submit, it will submit to an approving server and will compute the zkML proof. So as you can see, it takes quite a while, but it's not that long. So I think we went from about like 10 minutes or so to I think like less than about like 30 seconds. So you can get a pretty good result. And then afterwards, you can just submit on chain. Oh, I think my wallet is over there. Oh, sorry. Okay, I will submit a smart contract transaction on my phone, which is now connected via Wallet Connect. So it's like referring to my phone itself. Okay, it's successful. So you can actually go to Polygon Scan right now. And here was the transaction that got made. So you can see it submitted a score on chain. And if you decode like the transaction inputs, this basically the score and the proof bytes. So I will demonstrate an application on how you can actually achieve this with a Colab notebook. Okay, I found the seed. Great. Okay, as some of you might have asked, like, how do you actually do this at all? So I have came out a notebook that demonstrates how you can perform this AI ML techniques. So the purpose of this demo is to illustrate some learning objectives, like how can you actually train a toy model in PyTorch to perform classification. In this case, for the toy model we are using, we're going to use the iris model, which is a classical model in just classification tasks. And afterwards, we want to convert this toy model into ZK circuits and do it within Ezekiel, so you can do provable inference on chain. So you can get like the proof and that you can put in the smart contract. And also the third thing we want to achieve for this demo is like, how do you actually generate the solidity verifier? And how do you actually deploy it in Remix? Okay, so first step, we need to set up like the training data set. So I wrote the code over here. So it's just, you just need to import stuff over here. All right, for those who have access to the web, the Telegram chat, I've actually posted the demo over there. So if you want to follow through, like do follow along. So now we have imported the libraries. We can essentially load the iris data set from the scikit-learn library. And you can see like the data set. So in the iris data set, there are actually 3 kind of flowers that we want to classify, and it's going to be classified based on this 4 characteristics. And so essentially what we need is a neural network that takes in like 4 inputs and like shoots out 3 inputs, which either classifies between like 0, 1, or 2. So we can define like a simple model as such. So in this case, we're just going to do like 1 fully connected layer, 3 fully connected layers and 1 softmax output. And so what the softmax is doing is that it's going to pick like the highest neuron. So I'm going to create the model and initialize it. And so now we have the model. The next step that we need to do is then like split the data set into a training and testing set. So we'll just use like the scikit-learn libraries. So the good part about Python is that most of the things that you need to do in data science has already been done. So it's not like a problem that you have to solve. You just need to import things. So just run this and it splits nicely for you. And now once that's done, we can essentially start training. So in this case, we're just going to use cross entropy and your stochastic gradient descent and train it over 800 epochs. So it's quite fast because it's a small data set. So now we can actually then plot the performance of the model. So I think it's probably overfitted, but for the purpose of this demo, I think it's fine. And tada, you have just trained a neural network. So now we have a neural network that's trained. Like how are we going to put this into a ZK circuit? And this is where Ezekiel comes in. So for we need to import Ezekiel. Okay, it's now imported. And next, we just need to specify all the files that we need. And so to kind of kickstart the Ezekiel conversion process, first we need to kind of give a random input and also export the model as an ONNX file or ONNX file. Okay, that's pretty quick. And once that's done, we have all the ingredients to kind of generate our settings and also calibrate our settings. So this is required to create like the appropriate run parameters for like your ZK circuit. And calibrate settings does something really cool at the back end. So it basically helps you optimize like whatever that's settings that's generated for your particular neural network. So in this case, we're going to optimize for resources. So we don't really care about accuracy in this case. So we want it to prove quickly. So we just optimize for resources. And it's done. So next, once we have like the model, we have the settings, what we can do now is then compile the model. So this compilation steps saves a lot of time on the proving server itself. And with the settings, we can get like an SRS. So we need like the structured reference string to produce a ZK proof. And next, you would then call setup, and this would produce like two things that you would need. Like, so you have the PK and the VK, and this is required for you to essentially generate a proof and also verify a proof. Okay, that's pretty quick. And once that's done, you can generate the witness. And then afterwards, you can generate the proof. And in this case, we're going to use like the EVM front script since we're going to shove the proof into the EVM. And you can see that the proof got generated over here and have this long field of variables. Okay, I can't exactly, right. And you also have the instance and the proof. So the instances here is basically like the inputs and outputs from the neural network. And now we can then verify this proof. So it just shows verified. Okay, so now we have the VK and PK set up. So we essentially have like the ZK circuits. So up next, like we want to deploy this verifier and actually kind of use it on chain. So in order to do that, you need like solc in an environment, and we can basically just use solc select over here. And then once that's installed, you can generate the EVM verifier. Okay. So once we have like the EVM verifier, if you go to collect, you can actually find it over here. So you right click and save and download this. So it's here in my. So here's the code that Ezekiel generated. So this is the verifier that you can upload on chain and generate proofs from. So to test this out, you're going to use Remix. So I think I found Remix really convenient to use. So you don't need to set up anything, and it works out of the box. So this was the verifier I tested early on. So I can basically copy the code over and then go ahead and deploy this. So in this case, because I'm using sol C 0.8.20, so I'll just stick to this and compile the verifier. And for the purpose of this demo, we're going to deploy it on the Remix VM. And ta-da, it's deployed. It just works. Okay, so up next, we want to get like the inputs in a nice way. So we can install like the MCLBN library. Oh. Okay, so I can run this now. Okay, so we have converted the public inputs in the proof, and this is the inputs that you need from the neural net. So this came from like the random input that we have. So you copy this over. And copy this within Remix. and we click call. And it shows true. So like the proof works. And just to prove that's not a fluke, if we change like something like this from 2 to like maybe 0, it should fail. So you can't actually really tamper with like the zkML proof, and you can kind of prove this for yourself by just trying to, you could randomly generate values, and it's going to be quite tough to kind of find like the right set of inputs to map to the proof. So this is how you can kind of like show that the thing is probably safe, and it's going to be hard to reverse engineer ZK proof. And this is it for like the demo. And if you want to try this out right now, you can literally just use the Colab notebooks and try a bunch of the other examples that we have. So there's a catch with this particular setup. So in this setup, we like the proof accepts random values, and this might not be ideal for most applications. Let's say if you want some kind of data attestation source or like some kind of oracle mechanism. So for those kind of applications, you might want to use like a data attested verifier instead. So we have like a tutorial done for this, so you can also check it out within the notebook. And congratulations, guys. If you have followed through this demo, you'd have deployed a on-chain verifier that uses zkML. So it's quite feasible to use this for like hackathon applications, and our goal is to kind of make it easy for anyone to create a hack within like 1 or 2 days to demonstrate the use of like ZK applications in a smart contract. And I hope this clarifies like some of your questions on how can you actually do this right now. Are there any questions? Okay, that's it from my end.
Right. Thank you
Thank
very
you very
much. I saw there is a question in the chat box. I think maybe this question goes to both of you.
Collaboration. A couple of questions. So the first one is collaboration. Yeah, delighted to collaborate with anyone on particularly attested, signed, or otherwise verified inputs, and be rolling out some tooling that will help to connect those things up probably in the near future. And let's see, so the next one is, what are some of the security related things to watch out for while generating proofs and verifications? Well, there's a lot. I mean, one of the fundamental things is, what this can provide for you is a verification of an execution of a function, right? And you're allowed to control the visibility of the inputs and the outputs and the parameters. But we do give you enough flexibility that you might make some choices that don't make sense, right? So for example, you could set, if you set both parameters and inputs to be private, and they don't have any hash or any other attestation connected to them, then the function that you're actually asking someone to say is like, I know a set of parameters and I know an input that when combined produce this output, and that might not be what you expect, right? Another thing to think about is that a neural network by itself should not be used as a hash function, right? Neural network is kind of the opposite of a hash function in the sense that it's a function that's differentiable, right? It's vulnerable to differential cryptanalysis on purpose. That's what makes it useful, right? And so you shouldn't use an input to a neural network as a password, because if the network is available or even sort of lightly accessible, then someone might be able to figure out that password or what face satisfies that neural network if they have access to the neural network. So lots of things like that around the general crypto system that you're using. Anything you want to add, Jason? Security things to worry about.
Yeah, maybe we can take one or two more questions. And thank you very much, Professor. But can you also do me a favor? Every time when you answer the question, can you repeat the questions? Because some of the students, they may not be able to see the chat box. Great, we can take one or two more questions. And then any questions here offline as well? All right, then no more questions. So how about let's call it a day. Thank you everyone for attending this class, and thank you very much, Professor Morton, to give us this wonderful speech. Oh, we have one more question in the chat box. So for yeah, let me repeat it.
Yes,
so
memory is a huge problem, huge bottleneck. All I can say is that, okay, so the first time we verified MNIST on Ethereum, which was about a year ago, it took 450 gigabytes of memory. Today it takes 180 megabytes for the same model. So mainly we're just trying to be more clever and reduce that memory bottleneck. I think we've got a large improvement already, and I think we have quite a bit more juice left just in thinking through. And this is just, like I said, it's just engineering. It's like you look at the way the code works, you say, okay, do I really need this whole data structure to be in memory, or can I pipeline it? Can I think about, cache lines? Can I think about streaming the file access, this kind of stuff, right? So we're working very hard to make it sit memory. Should be a lot of improvements continuing to come, but yes, it still uses a lot of memory. And the good part of that is that if you work in this field, you have a really good reason to buy computers with lots of RAM, which is also very fun.
Great. For those of you who don't know, what the previous question is, so let me repeat the
Oh, I'm
previous
sorry, I
question.
didn't repeat.
It's totally okay. Yeah, so the previous question asked for generating ZK circle proofs. Memory seems to be another bottleneck. So how do you address this issue in the consideration? Yeah, so that's, thank you, Professor, for the answer just now. Great. Yeah, perfect. If there's no more any other questions, maybe we can call it a day. And thanks everyone for attending this class. Thank you, Professor, for your time as well. Stay tuned.
Yeah.
And also another announcement regarding to our hackathon is, regarding to our hackathon is we're going to start our hackathon next Monday. So actually you can already register the hackathon now through our link. Later I'm going to send the link into the our group chat, and we're going to announce and start our hackathon on 14th. And the hackathon is going to run for about roughly a month. So we'll have our demo day in September. Great. Perfect. Thanks, everyone. Thank you. Thank you. Thank you, Professor.
Anybody who wants to use Ezekiel, and we would love to. We would love to help you throughout that hackathon. We're pretty good at the 24/7 service and bad boundaries between work and life. So just ping us, and we'll help you out. All right.
All right. If anyone has questions offline, I'm actually in the venue right now in a different room, and I can actually address your questions and walk you through code in person. Oh, I've also posted links in the Telegram chat if you missed the QR codes.
Yeah, great. Thank you. Bye-bye.